effectiveness of continuous hydrogen production using integrated PV electrolysis storage systems. And just a quick announcement, the talk after that would be will change. The original speaker didn't show up, so we are going to have a talk on solar power system using chemical leaking combustion, but I'll introduce later. So now let's welcome Henry for the...
Thank you very much for the introduction, and thank you, Magnus. So I think it was a good segue. So we are working on the similar projects, and we should definitely collaborate more. I am a research scientist here at MIT Energy Initiative, and so this is a work done in our group. So Darik is one of the people working on this. Patrick is an undergrad, very talented undergrad, so he's also working on this. And Frank was our director of research. So what I will be talking about is, again, on hydrogen cost and how we can use hydrogen cost effectively to meet the potential demand of hydrogen. Before talking about the cost numbers, I want to give you an idea of why we need hydrogen. So when we look at the decarbonization targets that we are always talking about, going to 90% reduction in carbon emissions, so on and so forth, what we are always omitting is actually the progress that we have so far seen. I will give you an example from the US. When we look at the carbon emissions from 2010 to 2017, so this graph is showing different sectors and how their emissions are changing. When you look at transportation, industry, and residential and commercial, what we see is actually the emissions are not going down. They are either steady or going up. The only reduction in emissions we are seeing is in electric power system. So what does that mean? Actually, we are all our so far progress in decarbonizing the economy was in electric power system. Moving forward, what are our potential pathways? One is electrify everything, and this is a very hot topic. Everybody is talking about. We need to move to EVs, and we need to electrify industry, so on and so forth. There is a potential for that, but there are limitations. For industry, for example, you need high temperature heat. Whether you can use electricity for this is questionable. For transportation, light-duty vehicles, probably we can electrify, but when you talk about heavy-duty vehicles or airplanes, this is a very challenging target. So we need a molecule, a chemical that which is much more energy dense than electricity and battery energy storage to really complete this decarbonization target. And hydrogen is a natural choice because, first of all, you can produce from electricity and other sources with zero or near zero emissions. And you can also convert back it to electricity and other products, and it can fit well for all these applications that I've just mentioned. And when we look at the current hydrogen production, so we've already talked about this. I will briefly talk and then move to the next slides. But current hydrogen supply is mostly fossil. In the US, it is dominated by natural gas, but it is very regional. When we look at China, for example, it is coming mainly from coal gasification. So this is not only there is no only one source of energy source that we are producing today. And on the demand side, if you can see from this graph, almost 65% of current demand is for chemicals, 25% are for refining, and 10% other industries. So current applications are mostly industrial for hydrogen, and the total global demand, the energy content is around 8 exajoule. To give you a perspective, US total energy demand in a year is around 107 exajoule. So the hydrogen market is still quite small. When we look at the scale of hydrogen infrastructure, because one of the main issues that everybody is bringing up is about the pipelines and how we will be transporting hydrogen and storing hydrogen. So it is not a novel technology. We have hydrogen pipelines in the US and globally. We know how to store it, so on and so forth. But the main issue is scale. So when we compare with natural gas, hydrogen storage is around 1 million gigajoule. And when we look at the natural gas storage, it is like 4 orders of magnitude higher than that. When we look at this pipelines, it's around 1,600 miles. For natural gas, it is 300,000 miles, and for petroleum, it is 130,000 miles. Number of refueling stations, and these numbers are US. Number of refueling stations, there are 39 in the US and 100 in Japan, and 168,000 refueling stations for other energy sources. These are basically gas stations. So there is a huge scale difference here that we are talking about. So if we want to move to hydrogen economy or use hydrogen more in our daily lives, then first of all, we need to come up with a way of producing hydrogen in a cheap manner. And what are our options? So on the more experimental work, we've talked about how we can produce, and Magnus talked about using natural gas as well with carbon capture, so on and so forth. And this is showing the superstructure of how we can produce natural gas. So there are mainly 2 scales. One is centralized, the second one is distributed and smaller scale hydrogen production. And for both pathways, we have options. We can use electricity with electrolysis, and the electrolysis can be centralized or distributed. And on the natural gas side, we have a similar choice. We can do centralized SMR, steam methane reforming plants, or distributed production with smaller autothermal reactors, reforming plants, so on and so forth. And another way is using coal or biomass with gasification. These applications can only be for large scale. But when we look at the entire value chain, we also need to take into account the distribution and storage. And here also we have different choices. We just need to take into account all of these options to have a holistic approach. And so today I will be focusing on the electrolysis, low temperature electrolysis, and I will also give some data on the natural gas reforming side. And as I mentioned, in the US, 95% of the hydrogen is coming from natural gas reforming, and there is only one plant with carbon capture. But if we look at how we can produce natural gas-based hydrogen, so we basically have a reformer, and we need to shift the reformed gas towards hydrogen. We can capture CO2 here. We can further shift it to hydrogen and then capture CO2 here. So there are mainly 3 options, 3 places that we can capture CO2, and the cost of CO2 capture for these kind of plants is around 60,000 per ton of CO2 captured. When we look at the current CCS plants, there are 2 large-scale plants. One is Port Arthur in Texas, and the CO2 is used for enhanced oil recovery. So we are recovering more oil with this CO2. And there's one in Alberta, Canada. CO2 is sequestered. And there are 2 small-scale. These are more like a pilot plants that we have in Japan and France. And so when we look at the cost estimates, so here I am summarizing 3 studies. So for SMR-based natural gas price, it is around $1 to $1.2 per kilogram today. And when we add CCS, the cost goes up a little bit, but it is not really significant. So we are still looking lower than $2 per kilogram of hydrogen, even with carbon capture and storage. And if we add the levelized cost of storage, we are still within the same ballpark. So we are adding some cost, but when we compare to electrolysis cost that I will be showing, this is still very cheap. And there was a new Nature Energy article on the electrolysis and then cost projections for hydrogen production and using electrolysis with different technologies. And here, basically, based on these numbers and also other references, we are using in this study 2 electrolysis costs. One is reference cost, looking at 2020, 2025. time frame, it's around $800 per kilowatt, and the low cost is around $300 per kilowatt. This is a very optimistic projection that we are taking for our analysis. So before moving to the cost calculations using PV, so I will be talking about a electrolyzer system that takes electricity from grid and then produces hydrogen. And then we are not storing hydrogen or doing anything with hydrogen. So this is basically a mechanism just to produce hydrogen. And the application in our mind is mostly industrial or for fueling station applications. But the compression is not included in these numbers. So for a reference scenario, here the levelized cost of hydrogen is, depending on the cost of electricity, is anywhere between $2 to $3 per kilogram of hydrogen. And so for the low-cost scenario, actually, we are looking at $1.6 to $2.5 kilogram, depending on the different KAISO nodal prices of electricity. So, but when we use the grid, actually, the carbon emissions of producing hydrogen are quite high. So even if California, which is one of the greenest states in the US, when we look at these numbers and then use calculate the CO2 emissions intensity, we are looking around 240 plus kilograms of CO2 per megawatt hour of hydrogen. And when we compare this with the natural gas with SMR without carbon capture, we are still much higher than the SMR case. So current grid is quite dirty, and what we can think here is actually most of the US grid is based on natural gas based electricity generation. And if we think from a systems perspective, what we are doing is we are taking natural gas, converting to electricity, and then converting to hydrogen. The alternative is using SMR, which is taking natural gas and directly converting to hydrogen. So because of the higher number of steps, actually the SMR case is still less carbon intensive for the US grid. This is particularly in California case. But when you move to greener grids, and if you have more renewables and then your average grid is lower than natural gas-based electricity generation, then actually this will go down and then it will start competing with SMR with CCS, for example. So what we have looked at here is we've also taken a PV system and then used an electrolyzer to produce hydrogen. And here we are comparing, so the main issue with electrolysis and only PV is you need to have a larger PV plant to run the electrolyzer because of the change in intermittency and variability of PV generation. And so here we are looking at the ratio of electrolyzer to PV capacity for one location, and then calculating the levelized cost of hydrogen for different annual PV capacity factors. And here you can see as we go to lower capacity factors, we need larger electrolysis system compared to PV, and we are seeing the same trends, and then these are showing some cost values. But here there is a big difference when we compare these numbers with SMR, because for any of these plants, the capacity factor is around 20 to 30%, but SMR is around 95% capacity factor. So there is no apples to apples comparison. So to address this issue, what we have done is we have designed a simple model that takes into account PV, battery energy storage, if we want to use battery for electricity storage, an electrolyzer, hydrogen compression and hydrogen storage, and hydrogen supply. So by having this approach, what we are doing is we can operate the overall system with 95% capacity factor. And supply hydrogen to an industrial facility, which is much more similar to a SMR plant. So To solve this problem, we take the hourly PV and PV generation data from California and other locations in the US, actually almost 1,500 locations in the US, and we have solved this optimization problem hourly. And here I'm showing an example hourly operation, how PV capacity is changing relative to PV availability. So blue bars are the available ones, and yellow or orange lines are the PV use. And similarly, we are calculating at every hour how much hydrogen storage we need to have, and how we are depleting the storage or charging the storage, and how much battery energy storage we are using for storing electricity, so on and so forth. So with this, we are looking at a system plant availability of 95% of the time. We assume a plant hourly flow rate of 500 kilogram per hour, and annual PV curtailment is around 25% of total available resource. So we are not selling the extra electricity that we are producing. So what we have done is we have looked at the entire US, and we've solved this problem for 1,500 locations in the US, and then we calculated the cost of hydrogen. And first of all, on a depressing note, if we want to use solar for hydrogen production, the locations are quite limited, so we will be staying in the southern part of the US. But on the optimistic side, actually, we can produce hydrogen even with this setup, with the low-cost scenario, around 2.5 degrees to $2.5 to $3 per kilogram of hydrogen. So these are not super expensive compared to SMR case, although it's almost double. And another interesting observation that we have here is that it's really hard to see here, but these locations that are marked with green are showing the current hydrogen production facilities in the US. And what we see is most of these locations are very well aligned with the potential lowest cost hydrogen production places in the US with solar. So this is also showing a good motivation. Oh, here you can see it much easier. So these dots are showing the current hydrogen production locations, and these are quite close to where we can produce at a lower cost. And we can use the existing infrastructure, because they have, first of all, they have the sinks, they have industrial facilities, and also they have the infrastructure, pipelines in the Gulf Coast as well as in California. So we have also looked at other details, not only hydrogen production, but how the design of the overall plant is changing by location and availability of resources. And we have here we are showing two graphs. One is looking at how electrolyzer versus PV capacity ratio is changing with average PV capacity factor. So we are seeing a much more linear relation here. So as we go to higher capacity factors, we need to build a higher electrolyzer ratio to PV ratio. And for hydrogen storage, the trend is not as much as there. So here what we have observed is instead of capacity factor, we need to look at how much variation we are seeing in a year in the availability of solar generation to actually come up with the right hydrogen storage numbers. And I think I need to wrap up. So I will wrap up then. So basically we need, first of all, we need hydrogen to really decarbonize the economy. And we can design optimal designs for lowering the cost of hydrogen using PV systems. But of course, this is looking to a very specific application, and it is the beginning of a study. So we are currently working on many projects with some industrial partners as well as some government agencies to further analyze these systems. And if you have any questions, I'll be happy to answer your questions. And please feel free to email me as well if you don't see me around.
Can we take a quick question and then we'll transition?
As you said, you are looking for the scale of the hydrogen usage around over states. But have you ever thinking about the flammability and the safety issue that you can have to using hydrogen in a larger scale?
Yeah, so actually this is one of the challenges. If especially you will be using hydrogen in residential, or if you will be having a larger hydrogen infrastructure, that is an issue. But the flammability, more than flammability, the main concern is about leakage, because hydrogen is a very small molecule and you need to really seal everything to prevent leakages. But on the other hand, it's a small molecule and it is very light, so it directly goes to upper atmosphere. So you don't see the main problem that we are seeing with natural gas. It doesn't accumulate and then you can explode. But of course, there are safety concerns, but I think there are ways of solving these problems.
For example, for fuel cell usage, you are saying $2 per kilogram hydrogen would be affordable?
So if we can go down to 2 kilogram with $2 per kilogram, I think it's quite a competitive number with the natural gas pathway. But on the so for natural gas numbers, usually okay. So there is one part to this is for electrolysis systems, you can have a distributed generation. So you can be close to your source. And for the SMR numbers that we are citing, we are not including the cost of transporting hydrogen. So actually, to have a apples to apples comparison, for example, if you have a fuel filling station and you have a close by hydrogen production from an electrolysis system, it can be cheaper than producing centrally and then shipping it to you. Thank you.